Okay, my pre-calc little tiny babies, you're almost toddlers, right? Because you are almost done with this class. So you're growing up quick. Let's jump in to the last section, section 3, chapter 10, geometric sequences and series. All right, so let's start with what we've seen in the previous videos. So in the previous video we were talking about arithmetic formulas, right? And we we wanted to have a formula for finding the nth term, and we wanted a way of adding up an amount of terms, and both of those required us to know how the terms in the sequence changed from one to the other, right? The common difference. Now, the questions are the same, but the sequences are different. So now the sequences are going to be geometric formulas, right? Geometric sequences. But we still are going to want to find the nth term. We're still going to want to be able to add up the terms in the sequence. And just like arithmetic formulas, we're going to need to know how the terms change from one to the other. Now, for arithmetic, recall that this was we refer to this as the common difference. Right? So if D was 3, that would mean you add 3 every time you go from term to term. But for geometric formulas, we refer to this as the common ratio. Okay. So let's jump in. The first thing we're going to do is use that formula for finding the common ratio. And then I'll write that a little bit clearer in just a second. Ready? So the first example asks the question, can you find the common ratio given the following geometric series? All right, so we're going to start. We're going to start by noticing that a sub 1 is 2/3, and that a sub 2 is 1/6, and so forth. But our goal is to figure out how are we going from one term to another, right? I mean, how does 2/3 turn into 1/6? And then how does 1/6 turn into 1/24? Well, that's a good question, and that is the question of the problem. So the goal is to find the common ratio, R. Let me write the formula, because it's very simple. It's going to be a sub n divided by a sub n minus 1. So, in other words, we're going to take a term in the sequence, in the series, and divide it by the previous term. So let's do that. So let's take, in this case, we'll take the second term, which was 1/6, and we'll divide that by the previous term, which is 2/3. Right, so that's not bad. So 1/6, we will flip, we will multiply, and that gives us our common ratio, 1/4. So how do you get, so let me answer the question, how do you get from 2/3 to 1/6? Well, simply multiply by the common ratio. Right? So if you multiply by R, you'll move from term to term in this set. And so that just reduces to 1/6. All right, so let's see what else we can get into. So the next example says, okay, well, can you write the first 5 terms of the geometric sequence if they give you the following information. They tell you what a sub 1 is, and they tell you what the common ratio is. Okay, so remember, you want the first 5 terms. All right, so in other words, we want a sub 2, a sub 3, a sub 4, and a sub 5. Okay, so the formula, and I will, I'll go ahead and show you here. It's just, well, the recursion formula that was written on the previous page looks like this. A sub n is going to be equal to the common ratio multiplied by a sub n minus 1. Okay, this is nothing that you haven't already seen. I mean, all you're going to do is take the previous term and multiply it by r. So this is going to be, so r times a sub n minus 1. So this is going to be 1/4 multiplied by, what's the previous term? Well, the previous term is 24. So in this case, a sub 2 is going to be 1/4 of 24, which is 6. All right, and now to get the next term, again, just take the same 1/4 and now multiply it by what? By what? The preceding term. So 3/2. Now I'm just going to go ahead and answer the next two for you. So if you continue in this fashion, you should get 3/8, and you should get 3/32. Okay, so assuming my arithmetic is okay here, then we are all done with the problem. All right, so not that bad. Let's keep going. So in the next example, they ask, all right, if I give you the very first term in the geometric sequence, and I give you the common ratio, which is -1/2. Can you go from the first term to what they want, which is the 30th term? Okay. Well, this is not that bad to do. All I'm going to do is first I'm going to rewrite a formula that was on the previous page, right? And that is the formula for the nth term of a geometric sequence. So a sub n is equal to what? It's equal to a sub 1 multiplied by the common ratio raised to the power of n minus 1. Okay, I want to make sure you understand. I know that sometimes you see these, like it looks like a sub n is written in different ways, because it is written in different ways. It's due to the fact that, do you want to use the previous term to get the next terms? Well, that, if you can, but that would be the recursion formula. Do you just want to be able to jump right to whatever term you want in the sequence? Okay, well, as long as you have the first term and the common ratio, you can do that using the general term. Okay, so let's go ahead and make sure we understand. So all I'm going to be doing is plugging in -1/2 for r, and I'm going to be plugging in what? I'm going to be plugging in 4,000 for a sub 1. I'm going to do that right now. So that's multiplied by r. Oh, I said I was going to plug in, didn't I? So that's multiplied by negative 1/2 to the power of, and I'm going to leave this as n minus 1 for just a second. Okay, so we know the first term, we know the common ratio. So if you want to finish this, all that we're going to need to do is, well, it just depends on how many terms do you want us to go out. Like what term are you looking for? Well, we are looking for a sub 30, the 30th term in that sequence. So we're going to plug 30 in for the n. All right, so that's going to be 4,000 multiplied by negative 1/2 to the power of what? To the power of 30 minus 1. Right, so to the power of 29. All right, so at this stage in the game, I would normally call upon one of you to pull out your calculator and multiply that out. It should be well, let's see here. It should be a very small number. I don't have a scientific calculator in front of me, but I did have a chance to write it down before I started the video. It should be negative 7.45 times 10 to the power of negative 6. Again, so assuming that I plugged everything into the calculator correctly, then that should be your result. All right, well, what else can we get into? So let's see if we can find the nth term formula, right? The general term formula, if they just give us some terms in this geometric sequence, right? So the sequence starts out as, and I'm going to label right over top of it, right? So a sub 1 is 5, a sub 2 is negative 1, a sub 3 is 1/5, a sub 4 is negative 1/25. Right, so, all right. So to do this, what's required of us is that we first find the common ratio, right? We need to know the common ratio here. And to find the common ratio, if you recall, right, so I'll grab from the previous page. So it's a sub n divided by a sub n minus 1. Okay, so let's do this. So we're going to take, well, let's just take the second term. So that would be negative 1, and divide it by the previous term, which would be positive 5. So negative 1/5 or negative 1/5. That's our r. Okay, so the general term, if you recall, it's going to be, let me see if I actually, let me just try to make this easier on me so I don't have to keep going back and forth. Ready? All right, so if you want to find the general term, you're going to need to know what? You're going to need to know the first term, and you're going to need to know the common ratio. So a sub 1 in this case is 5. So ready, let's finish this up. So a sub n for the general term is going to be 5 multiplied by r, which is in this case negative 1/5, raised to the power of n minus 1. Okay, so I'm positive that you already know what I'm about to tell you, but just make sure you follow your order of operations, right? You're going to have to evaluate the exponent before you multiply by the 5. All right, now your recursion formula, I think they asked for both. So that's the general. The recursion formula would be a sub n. So a sub n is going to be equal to r times, so r would be negative 1/5, times the previous term. So a sub n minus 1. Okay, so these are our two formulas for a sub n. Okay, so what if we actually want to be able to start adding up some numbers, right? So what I'm going to do, right now, let's actually see if I can just take, actually I'll leave that there. Let's see if I can take the formula for the sum of n terms of a geometric sequence. And we're going to talk a little bit more about, we're going to use it first, and then I'm going to come back and I'm going to talk a little bit about what's happening here. Okay, so notice in this case, the sum formula requires that we know the following information. We need to know what the first term is. We need to know what the common ratio is. And we need to know how many terms you're asking us to add up. So let's go through this. So the first term is 4. How many terms are you actually adding up? That's 12. But let's go ahead and find r. So in this case, r is going to be, let's go ahead and take negative 12 divided by the previous term, which is 4. So r is equal to negative 3. Okay, so ready? So armed with this information here, we can add up the first 12 terms of that sequence. Ready? Let's do it. So s sub 12 is going to be equal to what? 4 multiplied by 1 minus, now here, be careful here, r is a negative number, correct? So that's negative 3 to the power of n. What's n? 12. Divided by 1 minus, and again be careful here, r is a negative number, 1 minus negative 3. Okay, so as long as we're careful with the treatment of our grouping symbols, then the sum of the first 12 terms, by my quick calculation, should be negative 531,440. All right. So let's chat a little bit about this sum formula, okay? And let's, if you don't mind, let's play a game. So if you have your calculator at hand, try something. We're going to do a little experiment. So take, for example, 0.99 and 1.001. All right, now both of these are very close to each other, right? 99 cents, well, it's a little bit less than $1.01. But the idea is these numbers are very close to 1. And what we're going to do is we're going to take both of them and raise them to you can pick whatever power you want. Just make it very large. And let's see what happens. All right, so if you take 0.99 and you raise it to the power of, let's say, 1,000, on your calculator, then roughly you're going to get something like 0.0000432. Okay, so a very small number. Now, if we do the same thing, except now we're going to take 1.001, and I just arbitrarily chose it to raise it to the power of 9,000. Then we're going to get approximately, I believe, 8,066,726. And now what I'd like to do is see if we can generalize this experiment, right? This is by no means offering a proof to the statement I'm about to make, but let's see if we can generalize this experiment. So what can we say, right? Let's go back to the 0.99. And let's say to the power of n. So the question becomes, what can you say about the result of 0.99 to the power of n as you let n grow very large, or let's say as you let n approach infinity? Well, you could try it, right? You could instead of picking 1,000, try 0.99 to the power of 2,000 or 3,000, 10,000. What you will find is this number, the result, keeps getting smaller. So then will you agree with me with this statement that as n approaches infinity, the 0.99 to the power of n is going to approach 0? Okay? Now, we're not going to make this is going to be the generalization, the statement that we're going to make. Maybe you could talk about trying to make a statement about what happens as 1.001, what happens to it as n approaches infinity. But what you would be able to say is that it approaches something. We don't know if that something's going to be the infinity or not. But so that's not the point. The point is, let's see if we can make a generalization about the following result, about when the 0.99 to the power of n, as what it approaches as n approaches infinity. And let me see if I can make sense of this for you. So here are two different formulas, and both of them give you the sum. I think you're going to agree with me the second formula looks like that's a whole lot easier to work with. And now let me make a statement, and let me show you. I can go into more detail if you'd like. But the idea is as follows. The r raised to the power of n, if you let n approach infinity, then r to the power of n approaches 0 as n approaches infinity, assuming that r, I'll write it this way, the absolute value of r is less than 1. Right, I hope that doesn't trip you up too much. All that's really saying is, look, if your r value is somewhere between -1 and +1, right? If it's a fraction, if r is between -1 and +1, like a half or -1/2, then if n is going to infinity, then r of n is going to 0. So can you see how if I make this term right here 0, can you see how the first formula can turn into the second formula? Right? That would be a sub 1 times 1 minus 0, or a sub 1 times 1. So you have two different sum formulas. They both work, but the second formula will work if this condition is held, right? So only if the absolute value of r is less than 1, meaning r is between -1 and 1. Now, why take all that time for that explanation? I could have just said, look, just here's a formula, just start to use it. Well, I want you to understand that where we're going right now is I want to add up an infinite amount of numbers, right? And what is interesting is how can it be that if you add up an infinite amount of numbers, you would get a finite result? So that is where we are right now in this problem. And let me go back to a teaser that I gave at the end of the last video. Can you actually show that 0.3333 forever, ad infinitum, is equal to 1/3? All right, well, let's see if we're up to the task. Let's see if we can do it. Well, first off, let's think about how can we interpret 0.33333 forever? Well, we can actually think about it as 0.3 plus what? Plus 0.03 plus 0.003. Are you with me? That we can think about this as an infinite sum, an infinite amount of summation. But okay, well that's okay because we have a formula that will do sums. But that formula requires that we know the common ratio, right? So in other words, we got to figure out how do I go from 0.3 to 0.03, and then how do I go from that to 0.003? So I need to find out what r is. Well, in this case, if you take 0.03 divided by 0.3, you'll find your r value. So in this case, your r value is going to be equal to what? It's going to be equal to 10 to the power of -1, or in other words, r is equal to 1/10. Right? So if you take 0.3 times 1/10, you'll get 0.03. You're just dividing by 10. Okay, so now we're on to something. So the question now becomes, I want to be able to find the sum, S sub n. But am I going to be required to use the first sum formula, right? Because I have two choices up here. Or can I use the second formula? Well, let's look at r. Is r between -1 and +1? It is. So then I can use the second formula. So the second formula is a sub 1 divided by 1 minus r. So the first term, let's agree that the first term in that sequence, a sub 1, is equal to 0.3. So let's plug it in. Ready? So that's 0.3 divided by 1 minus 1/10. Right? 1/10 is like a dime. So if you have $1 and you take away a dime, you have what? You have 90 cents. Well, what is 0.3 divided by 0.9? Well, you know the deal. You move the decimals. That's just 3/9, which is what? 1 1/3. So the statement, in other words, listen, look what you just did. If you find yourself tutoring some individual and they say, is 0.33 forever? How is that really 1/3? Well, unfortunately, they should not have asked you that question, right? Because they might be sorry, but we were able to show that it is indeed 1/3. All right, we are going to conclude. That is the last bit of theory for this class. I hope you were able to take away some information, and I hope you'll continue in your study of mathematics. It is the truth. It will, I don't want to say set you free. I don't know what that means, but it will train you. It will train your mind. It is a beautiful yet unforgiving science. And I hope you continue in your studies, and I will see you soon.